Hello everyone, my name is Dmr Tt and I'm a CSC data science student at Iare Hyderabad. In this video, I'm going to explain about the task-based effectiveness of basic visualizations. Abstract. Visualizations of tablet data are widely used. Understanding their effectiveness in different tasks and data contexts is fundamental to scaling their impact. However, little is known about how basic tablet data visualizations perform across varying data analysis tasks. In this paper, we report results from a crowdsourced experiment to evaluate the effectiveness of five small-scale 5 to 34 data points, two-dimensional visualization types, data table, line chart, bar chart, scatter plot, and pie chart. Across 10 common data analysis tasks using two datasets, we find the effectiveness of these visualization types significantly varies across tasks, suggesting that visualization design would benefit from considering context-dependent effectiveness based on our findings. We derive recommendations on which visualizations to choose based on different tasks. We finally train a decision tree on the data we collected to drive a recommender, showcasing how to effectively engineer experimental user data into practical visualization systems. Index terms, information visualization, visualization types, visualization effectiveness, graphical perception. Introduction. Visualizations aim to enhance understanding of underlying data by leveraging visual perception, evolved from fast pattern detection and recognition. Understanding the effectiveness of a given visualization in achieving this goal is a fundamental pursuit in the visualization research and has important implications in practice. A large body of prior research evaluated the general effectiveness of different visualization types. Guidelines and insights derived from these earlier studies have significant influence on data visualization today. However, these studies are conducted under conditions that were inconsistent across studies, with varying sample sizes, a limited number of tasks, and using different data sets. Research indicates, however, that effectiveness of a visualization depends on several factors, including task at the hand and data attributes and data sets visualized. For example, while one chart might be suitable for answering a specific type of question, example to check whether there is a correlation between two data attributes, it might not be appropriate for other types. Example, to find a data type with the attributes highest value. Here, we know little about the knows how some of the basic visualizations perform across different visual analysis tasks. So data representation is a main component of information visualizations. The fundamental focus of data representation is mapping from data values to graphical representations. Visualization designers use elementary graphical units called visual encodings to map data to graphical representation. Through human subject experiments, researchers have investigated the effects of visual encodings on the ability to read and make judgments about data represented in visualizations. Although prior such as proposed models of visualization comprehension, little is known about the how visual encodings are designed parameters interact with each other or different data and task contexts in forming the overall performance of a given visualization. A large body of earlier work has also been studied the effectiveness of visualization types with common design configuration for a selected number of tasks. Study design. When designing when deciding which visualization types to include in our experiment, we balance the familiarity of the visualizations considered with the comprehensiveness of the experiment. On the one hand, we would like to have more generalizable results, which suggested considering a broad set of visualization techniques in our experiment. At the same time, we would like our study to have the members of the general public as our participants. This would suggest to include a set of visualization techniques which are understandable by all participants. Building on previous work on investigations on visualization techniques supported by different visualization tools, example Microsoft Excel, Tableau, Spotfire, ClickView, Adobe Analytics, IBM Watson Analytics. We decided to include five well-recognized visualization techniques in our study. In this study, we include bar chart, line chart, scatter plot, table, and pie chart. Datasets, selecting datasets. To create visualizations for experiment, we selected datasets where the participants were unfamiliar with the content, but familiar with the meaning of the data attributes used in the dataset. This is particularly important since we did not want user performance to be affected by how familiar participants are with the meaning of the data attributes. We first selected five different datasets: cereals, cars, movies, Summer Olympics medalists, and university professors. We then printed a part of each dataset on paper and showed them to six pilot participants, four male and two female. We asked participants, please look at data attributes used in each of these datasets. Which datasets can you feel contain data attributes that you are more familiar with? Cars and movies datasets were the ones that five out of the six participants select. The cars dataset provides details for 407 new cars, and the movies dataset provides our details for 335 movies released from 2007 to 2012. Data attribute types. Both data sets include data attributes of nominal, ordinal, and numerical types. We define nominal data attribute type as categorically discrete data such as types of cars, example sedan, SUV, wagon. Ordinal is defined as quantities, which is in specific range that have a natural ordering, such as rating of movies. The number of unique data values range from 6 to 12. We define numerical as continuous numerical data such as profit values of movies. We generated visualizations using pairwise combinations of all three types of data attributes available in our data sets. Nominal into numerical or ordinal into numerical data. Sampling. During our informal pilot study, we generated visualizations representing different number of data points ranging from 50 to 300 in increments of 50 data points. In this visualization, each visual mark, example a circle or a bar, represented a data point. We noticed our pilot participants face two challenges using static visualizations containing more than 50 visual marks. First, the participants and had difficulties performing some of the tasks. Example, compute derived value and characteristic distribution using static visualizations. Error rate increased, and in some cases, participants gave up. In addition, in some cases, participants had to spend more than 2 minutes performing the task. Due to practical limitations of conducting the study, example length and complexity of the experiment, with a high number of visual marks, we decided not show more than 50 visual marks at the time. We had two options for that, showing all the data points in our data sets. So here is the figure one about the five visualization types used in the study as we've seen before. In this figure, each visualization shows the average highway miles per gallon, a numerical data attribute for cars with different number of cylinders and ordinal data type. So first one is the scatter plot, which is having the highway miles per gram per gallon to cylinder. And second one is the bar graph. And third one is a line graph. And fourth one is a pie chart. And fifth one is a table chart of the cylinders and the highway miles per gallon used. Visualization design. To generate visualizations, we use three pairwise combinations of three different data attribute types available in our datasets. In particular, we use nominal into numerical, ordinal into numerical, numerical into numerical. We did not include nominal into nominal because it is not possible to represent this combination using all five visualizations considered in this study. Example line chart. To create scatter plots, bar charts, and line charts, we use the same length, font size, and color to draw the XY axis. In addition, all the visual elements, example bars in the bar chart, used in the three charts are the same two color. Unlike other visualizations, pie charts do not have any access to read the values from. That is, to create pie charts, we have to make design decisions on how to show values of two data type attributes used to generate them. The main design decision that we had to make for pie charts was whether to include legends. Instead of having legends, we could potentially have labels on the type of top of slices of pie charts. We tried to put the labels on the top of slices, but this caused visual clutter, particularly in cases where the labels were long. Additionally, using legends for pie charts is a common practice in majority of commercial visualization dashboards. We decided to not show any value on the top of the slices of pie charts, instead of showing the values of one data attribute using a legend and another one beside the slices. For tables, we separated different rows of the table using different light gray lines. We used a darker background color to make the labels. Two data attributes used for creating the table. So here is it. The first one is the retrieve value task, and second one is the pie chart of determining range task, and third one is the finding exterminal. First one is about the five type we've seen before about the average highway miles per gallon for five types of car, that is sedan and SUV. That is represented in the bar graph. The second is the pie chart, which shows the average budget for movies with different ratings. Movies with what ratings are the budget from? It ranges from 115 to 190. The third one is about the rating for movies with different genres. Genre was movie was the highest rating, shown in the scatter plot. Coming to data analysis. To analyze the differences between the among the various visualizations for each participant, we calculated mean performance values for each task and visualization type. That is, we average time and accuracy of questions for each visualization type and task. Before testing, we checked that the collected data met the assumptions of appropriate statistical tests. The assumption of normality was not satisfied for performance time. However, the normality was satisfied for log transformation of time values. So we treated log transform values as our time measurements. We conducted repeated measures analysis of variance ANOVA for each task independently to test for differences among the various visualizations data sets and their interactions with one another. While the visualization had significant effects on both accuracy and time, the dataset has no significant effect on accuracy or time. So here is a pairwise relation between visualization types across tasks and performance metrics. Arrows show the source is significantly better than the target. The first one is the finding anomalies, and second is the correlation, distribution, order, filter, finding clusters, derived value, find extremum, retrieve value, and determine range. So these are divided into accuracy, time, and user preference. This is shown as a pie chart, scatter plot, bar chart, line graph, and table chart. In what ways we can use the accuracy and time and user preference. We first give an overview of our analysis of the results and then discuss them in detail for each task. We provide detailed analysis of the results in table 1. Throughout the following sections, accuracy refers to values in percentages, and time refers to values in seconds. Results aggregated over task and data sets show that bar chart is the fastest and the most accurate visualization type. This result is in line with prior work of graphical perception, showing that people can decode values encoded with length faster than other encodings such as angular or volume. Conversely, line chart has the lowest aggregate accuracy and speed. However, line chart is significantly more accurate than other charts for correlation and distribution tasks. This finding concurs with earlier research reporting the effectiveness of the line charts for finding tasks. Nonetheless, the overall low performance of the line chart is surprising and for some tasks can be attributed to the fact that the access value ticks are drawn at intervals. This makes it difficult to precisely identify the value for a specific data point. While pie chart is comparably as accurate and as fast as bar chart and table, the for retrieve range order, filter, extremum, derived, and cluster tasks. It is less accurate for correlation, anomalies, and distribution tasks. Pie chart is the fastest visualization for performing cluster tasks. The high performance of pie chart. Conclusion. In this work, we report the results of a study that gathers user performance and preference for performing the common data analysis using the 5 small-scale 5 to 34 data points, two-dimensional visualization table types, table, line chart, bar chart, scatter plot, and pie chart. We use two different data sets to further support the ecological validity of results. We find that the effectiveness of the visualization types considered significantly changes from one task to another. We compile our findings into a set of recommendations to inform data visualization practice. Thank you.